Good evening, everyone. This is the NPTEL problem solving session for the course Robotics, Basics and Selected Advanced Concepts. This is the session for week 9, and we'll just go through the lecture notes of this week, and after that we'll just discuss some of the ways how to solve the assignment problems of this week. So yeah, we'll keep admitting people as they come in, and well, I'll record this discussion and this advice and then put it up on the channel. So yeah, so this week three things are introduced. Okay, so first one was motion planning. How is motion planning essentially approached? Like one way of doing motion planning, and then there was a discussion about the control of a single link, and then there was a discussion about the control of a multi-link serial manipulator. Okay, so for motion planning, uh, yeah, this time history, okay, is specified in the particular methodology that has been discussed in the lectures. Okay, so basically you specify the time history, okay, in either the joint space or the Cartesian space. So either you specify how the joints should move, or you specify how the end effector should move, and based on that you calculate the joint trajectories, okay, through inverse kinematics. Okay, so because in the end you can only move your joints, so either you plan directly on your joints, or you plan in the Cartesian space or the end effector, you plan for the end effector, and then you convert those end effector trajectories to joint trajectories using your inverse kinematics mapping. Okay, so yeah, like, and to do this, to do motion planning, you need to specify initial and final point, and in some cases via points are also introduced. Okay, so via points are just intermediate points between your initial and final position that you want your robot to pass through before going to the final position. And yeah, so there is a slight discussion about continuity. Okay, like what does continuity mean? So uh, like the number, okay, Cn, okay, or this italicized C raised to the power some number represents the degree of continuity. Okay, so I mean, how many times can you differentiate a function? I mean, how many non-zero derivatives of that function exist? Okay, so like for a constant function, okay, it is C1 continuous. Okay, and so if the continuity is only in the values, okay, it is called C0 continuity. If the continuity is in the first derivative, okay, if the first derivatives like are the same at all the points, okay, like they are consistent at all the points, it is called C1 continuity. If the second derivatives are consistent at all the points or exist at all the points, then it is called the C2 continuity. Okay, so usually we generate trajectories that have at least C2 continuity, okay, so that we can specify the accelerations as well, because again, if you specify the position, then you have to differentiate it twice to get the acceleration. Okay, so if you want to specify the acceleration, it has to be at least C2 continuous. Okay, so and then trajectory update rates. So they actually depend on how you are doing trajectory planning. Okay, so there are two methods. You can either do offline trajectory planning or online trajectory planning. And this update rate, this discussion is only relevant in case of online trajectory planning. Like how fast can you update your trajectories? Okay, because if you're doing offline trajectory planning, then you don't update the trajectories. Basically, you have already generated the trajectories and you track them. Okay, so Yeah, so now there was a discussion about joint space schemes. Okay, how to do motion planning in joint space. Okay, so yeah, like theoretically, infinite number of smooth curves connect from one point to the another in a, let's say, 2D Cartesian plane, right? Or between any 2 points in a, yeah, in a Cartesian space. Okay, so you can interpolate between any 2 points. Okay, and this, okay, this particular thing. Okay, this is okay. This is where the discussion of continuity, gets very important, because you see in this case the accelerations, okay, they are very large. Okay, basically there are discontinuities in the acceleration values. Okay, because the theta we chose to be, because the position we chose to be linear. Okay, so the velocity therefore has to be, a piecewise constant function. And since this is a piecewise constant function, whenever it changes value, there is a discontinuity in the derivative of the velocity. And this discontinuity represents it as these spikes in the acceleration graph. Okay, so to maintain C2 continuity, okay, like what we usually use is a cubic trajectory. Okay, so that we can specify even the acceleration, okay, linearly. So like this is a general equation of a cubic polynomial. Okay, and this time t, okay, that is the variable. Okay, it varies from t0 to tf. Okay, like in how much time you want to complete the trajectory, right? So if you want to go from, let's say, theta 0 to theta f, then when t is t0, then this equation should represent theta 0, and when t reaches tf, then this equation should give theta. Okay, so these are the boundary conditions that have been specified to actually calculate these coefficients. And since there are four coefficients, we need four boundary conditions. So along with positions, we also specify the rate of change of positions, okay, or the velocities at the initial and the final point, so that we have now four conditions and four unknowns to solve for, and that we can do analytically. Okay, and that has been given to you in this slide. Okay, so this is the like example of one such trajectory, okay, where you had been given some initial and final condition and some initial and final velocities as well. Okay, then there is this non-dimensional form. Okay, so what does the non-dimensional form essentially mean? Okay, if you see this A3, okay, and even A2, they are divided by TF squared and TF cube. Okay, so whenever TF are very large, okay, it can introduce some errors in the trajectories. Okay, so what we do is we like normalize the time. Okay, so we define a new variable that is time normalized, because then that u varies only from 0 to 1. Okay, and then we use u to specify the trajectory, because now you can only vary from 0 to 1. There is no arbitrary, because this tf can get arbitrarily large, but this u cannot get arbitrarily large. Okay, so basically you are just normalizing your time. Okay, and doing that also normalizes the coefficients. Okay, so now the coefficients look like this. Okay, where this all these relations they hold. Okay, and then there is this another way to write the cubic. Okay, so just okay. So yeah, I think this is mostly straightforward. Uh, yeah, so if we want to control the acceleration as well, not just specify the acceleration in a linear fashion, then you need to go higher in your order of the equation or the order of the polynomial that you use. Right now, you were using a cubic polynomial. That's why you could. That's why it was only possible to specify acceleration in a linear fashion only. If you want to specify, if uh, the designer wants to specify the acceleration in, for example, a quadratic fashion, then what they would need to use is a quintic or a fourth order polynomial. Okay, you can go as high as you want, but again, the more high you go in the degree of the polynomial, the more computations you have to do, basically for the calculation of these coefficients as well, and also for the online computation. Yeah, and then there is this case of introduction of wire points that has been discussed. Okay, so these wire points you can like choose the type of continuity that you want at wire points. Okay, so if you want to specify velocity, then you need to, you know, have C1 continuity at least. If you want, you know, to have a specified acceleration also at wire point, then the continuity at wire points need to be at least C2. Okay, so yeah, like these are the two cases that have been taken here in this lecture notes are when the velocities are specified and the velocities are not specified. Okay, so when velocities are specified, C1 continuity is ensured, like we discussed this, right? And when the velocities are not specified, even C1 continuity is not ensured, only C0 continuity is ensured. Okay, so that like introduces some very spiky motions, okay, or very jerky motions in our robot or whatever we are trying to control. Okay, so you see, this we since we introduced a wire point at t equal to 2, if you differentiate it twice, then at t equal to 2, this theta 1 will be discontinuous, as we can see from the graphs as well. This is because we have considered only C1 continuity. Okay, so it will only be continuous up to, you know, this value, okay, up till the values are matching. Okay, so this is C1 continuous. Okay, and now this is case 2. Okay, so in this case 2, okay, since it is not specified what kind of trajectory you want to use, okay, therefore you're free to choose. Okay, basically you can now break this problem of motion planning through a wire point in two problems, two different motion planning problems, where you have to go from initial position to the wire point and then from the wire point to the final position. So you can specify the velocity and the acceleration at the wire point such that it is continuous at both the left and the right of the wire point in time. Okay, so this is what has been discussed here. Okay, if you go through the lecture and lecture notes, it will be very clear. Okay, and then there is a discussion on Cartesian space schemes. Okay, so basically Cartesian space schemes are more natural. Okay, because end effector is the you know the link that you want to move, or that the operator wants to move. And so it is more intuitively simpler to design or to specify the trajectory for end effectors, right? And so it is easier to see, visualize, and everything. Okay. Yeah, so and there is a difficulty in planning the orientations of the end effector. Okay, and due to representation issues. What are the representation issues? Like what kind of representation you choose to specify the orientation will also, you know, constrain what kind of approaches you can use to do motion planning. Because if you use Euler angles, they become singular for some particular values of Euler angles. Okay, if you use quaternions, then you have to keep, then you have to make sure that they are always unit your norm. Okay, they are always normalized. Okay, so like that is where the difficulty comes in. Okay, the orientation part. Okay, so traditionally, two Cartesian space paths are used for position. One is linear and one is circular. Okay, so like they are just quite okay. So one is when the tool moves in a linear fashion between the initial and the final point, and one is when the tool moves or the end effector moves in a circular pattern when going from the initial to the final position. Okay, so whatever type of interpolation you end up choosing, all paths must be C2 continuous so that accelerations are not discontinuous or not very high. Okay, so this is for straight line motion. So basically you just specify a straight line. Okay, and since you have specified the straight line, that is essentially what you want to do. Okay, so you just need to uh, yeah, plan this x of t. Okay, because since you want to specify the 3D trajectory. Okay, so you can specify x of t, and then using the linear interpolation for the rest two axes. Okay, so this interpolation is for the other two axes. Okay, so yeah, you plan a cubic for x and you plan a linear for y and t, right? And then for circular motion, okay, this equation, I think yeah, like for smoothness, circular arcs are desired. I think Sarah might have discussed this more in the lectures. So yeah, nothing much here. And then there is a algorithm for circular interpolation also given. Then for orientation, Sir has discussed one parameter called Euler parameter. Okay, so like, you can just go through that through lectures also, or through some other uh, resources. Okay, then there is control of single link. Okay, so in this control, you've been shown first of all a model of DC motor. Okay, a link being controlled by a DC motor, and then you had sir had derived the shown you the equation of motion of this system, and then through this equation of motion, sir had went into the Laplace domain. Okay, so yeah, like this is the final equation of motion. Okay, and in compact form it is written like this. Okay, and from here, sir went into the Laplace or the S domain. Okay, so took the Laplace transform. That so this finally what was written is the transfer function of this system. Okay, so there are two transfer functions for two different inputs that are there. Okay, one is the torque, other is the voltage. Okay, so Yeah. So for control, what you do is you choose your inputs such that the zeros of your transfer function, okay, yeah, the zeros of your transfer function lie in the left half plane. Okay, so that is how you assume your, inputs to be. Okay, and this is like a linear feedback controller. Okay, yeah, like you calculate a constant gain. Okay, and you give a feedback or only the proportional feedback of the desired trajectory and the actual output. Okay, desired output and the actual output, you give the difference as the feedback, and then you multiply it by a gain, and that is what you have defined as your control input. Okay, so yeah, you can vary Kp from 0 to infinity. Okay, and again, uh, like between all these values from 0 to infinity, there will be or there might be some values of k for which the system becomes stable. Okay, so that is the idea of introducing control. Okay, if the system is not stable, or even if it is stable, if it is not controllable. Okay, so by introducing feedback and by choosing the parameters of your input such that the system after giving feedback becomes stable or controllable. Okay, and then there is just equations related to that itself. Okay, like what happens when like t goes to infinity, right? Things like that. Like what is the steady state value? Okay, and so this was, I think, for the first order approach. Okay, and yeah, so yeah, this is the analysis of a first order system. Okay, so basically a transfer function is the denominator is uh, degree 1. Okay, and for any physical system, a transfer function should be proper. Okay, and what is a proper transfer function? Where the order of the denominator is greater than, always greater than the order of the numerator. Okay, that is what we call a proper transfer function. And for any physical system, due to causality, I think Sir has also mentioned this, uh, for causality to, yeah, for a system to be causal, okay, the transfer function must be proper. Okay, like this statement means that the transfer function is proper. Okay, so yeah, like this was the analysis for a first order system. Okay, you can use what was done above to do analysis of this system, and then there was a analysis of a second order system. Okay, where we've just added a step input in this. Okay, so again, like analysis of second order system, you guys might be more familiar with these kind of systems because the most almost all of the physical systems are second order systems. Not all, almost all. Should I say majority of physical systems. Okay, for example, if you take spring damper system, or spring mass system or spring mass damper system, so all of them are second order systems. Okay, and this like also uses the second order system theory. Okay, so you can see some parameters, natural frequency, damping coefficient. Okay, and then there are different cases similar to the ones in case of vibrations. Okay, where your system response is underdamped or your system is underdamped, and when it is critically damped, overdamped. So all of this is given. Okay, and if you just go through lectures once, video lectures, then I think you will be able to grasp it really well. So just what is the difference between critical and overdamped is critically damped response is the response that reaches the desired state fastest without any overshoot. Okay, so without any overshoot, critically damped response is the response that will converge or that will, you know, go into a acceptable error range fastest as compared to the overdamped version. Okay, and yeah, if you allow for overshoots, okay, that is if you make your system underdamped, that will introduce some overshoots, but that will also cause your system to settle much faster as compared to the critical and the overdamped response. So you can design your systems to be either one of these, okay, either critically damped, overdamped, or if you can allow some overshoots, then it can be underdamped as well. Okay, and there are like these equations you can derive as well, everything. There is like you just have to solve the equation of motion, okay, and once you solve the equation of motion, you can just try to get the first basically amplitude when the velocity becomes zero first. Okay, so that is what will give you your peak overshoot. Okay, so like that is basically how you can derive all the results that have been given. Okay, so yeah, then there was this PID control for single link. So till now in the above example, you guys had seen only P feedback, right? Only the proportional feedback. Now, what they're talking about here is the PID feedback. Okay, the proportional integral and derivative feedback. Okay, now like there are methods to choose all these coefficients. Okay, KP, KI, and KB, right? So that the system basically, first of all, is stable and converges faster as well. Okay, so you can just go through this either lecture slides or lecture notes or through some other control systems book like Norman S. Neese or Franklin or maybe Ogata. You will get these concepts. Okay, and then there is a concept of digital control because most of the control today, like almost all of the control today, is done using digital computers. Okay, and digital computers, they do not understand continuous signals or they do not work on continuous signals. They work on discrete signals. Okay, and since in this image also you can see that there are significant variations when you compare your discrete signal to the continuous signal. Okay, and this digital to analog or vice versa, analog to digital conversion is done electronically. Okay, and that introduces delay. Okay, and that changes everything. Okay, so like this is just how sampling is done. This is just one example of a digital control system, okay, of a digital controller. Okay, and yeah, so basically for digital control, for continuous control, what we did was what we used S domain approach. Okay, Uh, that is the Laplace domain approach. For digital control, we use the Z transform approach. Okay, and for that again, you can see this textbook that Sir has mentioned, Franklin. Okay, so the title of the book is Feedback Control for Dynamic Systems. And then there is control for multi-link manipulator. Okay, so this is like very similar to what is already done, but just that it is done for multiple variables at once. Okay, so there is not much difference, I would say, in what will be done here and what was being done already there in the above examples. Okay, so you can just treat this as an example problem, okay, or a kind of generalization or extension of what you have read above to a 2D problem. Okay, so I think, yeah, and I highly suggest, as always, to go through some of these resources that Sir mentions. Okay, these suggested additional readings. Okay, they will help you gain a better understanding of the concepts that you're studying. So let me just go through the assignments once. Okay, so yeah, now this is something about continuity. Okay, so this is directly from the lecture notes. You can go through the lecture notes and you'll get the answers of most of the problems actually. Okay, is performed. Okay, now again, motion planning for the orientation. Okay, and then orientation, if you go through the lectures, like sir has discussed a particular orientation called the Euler parameter that he's using. Okay, and yeah, like all the this feedback control. Okay, like it is very difficult, like almost it is not possible to follow any trajectory exactly. Okay, so again, you can only follow a trajectory up to a desired accuracy. Okay, uh, but yeah, again, with and without external disturbances, your in both the cases your approach would be different. Okay, and this is a single link driven by DC motor. This is exactly the system that has been discussed in the lecture notes, so you can just go through that. And then there is this transfer function, okay, like of the same system. So yeah, you can. So basically, going through the lecture notes will tell you like pretty much everything you need to know to answer these assignments. Okay, and then just going through the subjective assignment. Okay, so they are just applications of again what has been discussed in the lectures. Okay, so there are initial and final position, initial and final rate. Okay, and you just have to obtain the coefficients in the first one. Okay, so this is like a direct application of what has been given here. Okay, either you can do this or you can do this, the non-dimensional, either the dimensional or the non-dimensional form. Anyone would work. Okay, and then again, this single link manipulator connected to a DC motor. Okay, so yeah, you have to vary Kp, okay, between 0 to 2 in steps of 0.5. So basically you have to test this for 4 different values. Okay, so you have to use Kv equal to 0, 0.5, no, I think 5 different values. Yeah, 0, 0.5, 1, 1.5 and 2. Okay, and just obtain the plots for theta. Okay, using the equation of motion. And how do you numerically obtain the plots? You integrate it. You write it in the state space form, as sir had discussed in the last week. Write it in the state space form. Okay, and then if you're using MATLAB, you can use ODE45 to integrate it. Okay, because ODE45 can integrate any equation that is written in the first order form. And we know already we can write any linear equation in first order form, linear differential equation in first order form. Okay, then again, there are similar questions. And for the additional question, no, let us come to fourth question. See, now here is where you can choose, where you basically choose what kind of damping you want in your system, as was being discussed in the second order system control. Yeah, okay. So here, these are the design choices. Okay, what should be the settling time? What should be the overshoot? Okay, so here he's specifying no overshoot. Okay, so basically, since there is no overshoot, it cannot be underdamped. It will either be critically damped or overdamped. Okay, so yeah, and then to make your Like easier, you can try to use the control system toolbox and PID tuner. And the additional question, it is like a similar question to the first one, but just with a via point. Okay. And at via point, the velocity has been specified. Okay, so this is case one of what was discussed in the lectures here. Okay. So yeah, this one. Okay, case one where velocities is specified. So yeah, I think this is pretty much all what you guys you know need to do in this week, and I'll upload this, and then we can meet next week for any other doubts that you might have. Okay.